Okay, so here let's say a little bit more about the boundary conditions. Let's still stick to the Poisson's equation and introduce how can we integrate the Newman and Robin boundary condition. A Robin means a mixed boundary condition into the weak form of the differential equation. So a Newman means the partial means let's say a partial U. Okay. So let me just say the gradient of the solution dot with the normal of the boundary has to be equal to something. Let's say A. Okay. Robin boundary condition means the normal derivative of the solution has equal to AU plus B, has to be equal to a linear function of the solution itself. So, for example, if you have a heat transfer problem where U is the temperature, the left-hand side, like the Newman boundary condition, means you have a fixed heat flux into the domain. The right-hand side means the heat flux is proportional to the temperature. Right, both makes some sense in some applications. And in structural problems, one is like you have a fixed slope, and the other is you have a slope. It's more like a spring. You have a slope that is proportional to displacement. Okay. So if you have this kind of boundary conditions, and we can integrate that boundary conditions into a combination of the weak form, of the bilinear form and linear form. If you have Newman boundary conditions, so let's do Newman boundary conditions first and do Robin boundary conditions second. So if you have Newman boundary conditions, the bilinear form of, now let me write U and V, is equal to L of V, right? So V is the function for any V, let's say within H1. So if we are looking at the Poisson's equation, remember when we get to the weak form after integration by parts, we only have first order derivative in both the test function, which we are saying like the function where the residual has to be orthogonal with, like the function that used to test orthogonality is called the test function, that is V, and U is like the trial function. It's called the trial function because I'm trying a solution with that function, and that is a surrogate for the solution. So U is the trial function, V is the test function that tests the orthogonality. And V is any function. The test of orthogonality is saying that the residual has to be orthogonal to any vector in the linear space. So like the test function should be any function in the linear space. So if I have Newman boundary condition, I should not modify my bilinear form. My bilinear form of U and V, it's still equal to the integration of the domain grad U dot grad V dx. But let's see how can we construct the bilinear form so that we still have the Poisson's equation. The Poisson's equation, let's write the divergence of the gradient equal to F, okay, with this boundary condition. So previously we have the linear functional. If we want to enforce this, we have L of V equal to integration over the domain of minus V times F dx. Right, because of the integration by parts, this negative sign gets cancelled out with the negative sign on the left, and we obtain the differential equation. But in this case, with the linear function, it has to be added with something on the boundary. It has to be added by something on the boundary, and let's say what this has to be. This is because once we add these two terms, once we equate the bilinear form with the linear form and perform integration by parts, we get minus the integral of we take the gradient from the v and put it as divergence in u times v dx, and here comes our boundary term. The boundary term, remember, when we are doing integration by parts, it is another form of the divergence theorem. So what comes out of the boundary term is the v is the normal dot with the divergence of u times v. Okay, so that has to be equal to L, which also now has the interior term and the boundary term. Okay, here's the question mark. Now we have two interior terms. And remember, v can be anything in the interior, right? So this that is multiplied on v in the interior better has to equal to this, which is also multiplied with v and integrated over the interior. That's because v can be anything. That gives us the differential equation, which holds inside the domain. And we also have the boundary term here. The boundary term is integrated only on the boundary, and it is again multiplied by an arbitrary v. And v, without the essential boundary condition, without the boundary condition of restricting the x, with restricting the function space on the boundary, v can also be anything on the boundary. So whatever that is multiplied by v on the boundary should also be equal to whatever that is multiplied by v on the boundary here. So we can now know if we want to enforce this boundary condition we have over here, if we want to enforce this one, we already have the left-hand side multiplied by v on here. Now we want to construct the right-hand side to be equal to a times v. So if we take this to be a times v ds, this is a times v ds, then we are properly deriving the boundary condition over here by saying that v has to be anything. So what is multiplied on v on the boundary has to be equal to whatever that is multiplied on v on the boundary on the other side of the equation. So this gives us the boundary condition. So this is how we if we know the boundary condition in the strong form, how do we deduct, how can we derive the equivalent weak form that is going to give us the right boundary condition in the essential way, not in the essential way, in the natural way. Like this is a way to derive the natural boundary condition. And for some cases, like Dirichlet boundary condition, there is no way we can derive the natural boundary condition by doing this. So we go back and enforce it strongly. We put it as part of the X and enforce it as a essential boundary condition. So there are two ways to derive boundary conditions in finite elements: the essential way and natural way. So this is, I'm teaching you how to do the natural way. The essential way is way easier. All right. Question? Yeah. Yes, I'm forming. Okay, so f is a fixed function, right? is the right hand side of the PDE. So it's a fixed function. It's a fixed function that doesn't depend on what v is. So instead of an integral of the function, this is a weighted integral of the function, right? It's like the previous case is a straight integral of the function that is a linear functional. In this case, we are weighting the function differently at different points in the space and then integrate. It's still a linear functional because if you multiply f by a constant factor, this L gets multiplied by the same constant factor. If you have f1 and f2, oh, sorry, I'm not talking about f here. I'm talking about v here, right? If you scale v by a factor, the L of v is also going to be scaled by a factor. If you have v1 and v2, then L of v1 plus v2 is equal to L of v1 plus L of v2. All of this is because f is not dependent on v. No. Here the definition of L is the summation between two terms. One term is a weighted integral of v in the interior. The other term is another weighted integral of v on the boundary. Yes. The L, if I have a different f or a different a, I actually essentially get a different L, right? Yeah, and this is only well defined in the Sobolev space, in H1 space. If you go to L2, like the boundary integral, it's kind of analogous to the value of the function we have in the one-dimensional case. So this L would not be a bounded functional in L2. So you have to go to the more complex function space to define this L to get the proper boundary condition. Okay, then the next task is this one. What if I want this Robin boundary condition? How can we modify whatever we are doing here to put that AU? How about if you are saying we modify this? Okay, so let's figure out what we need to add to the equation, right? And then let's figure out what do we need to do here. So first of all, let me actually modify this a little bit just to make the notation a little bit easier. Modification from the previous case. Let's switch the A and B here. Actually, A here, B here, so that like we can reuse the constant from the previous case, right? So we have a constant plus a linear function of the solution. Okay, then let's see if we want to enforce the interior integral should stay the same because I'm satisfying the same differential equation, but the boundary integral needs to change a little bit. Not only I have the A times V term, not only I have the A, but I also have a BU. So this A here should become A plus B times U. Or the additional term I need over here is integral over the boundary of A times U, not A times U, of B times U. Yes, so where does this belong to? Let's take a look at this. Is this a linear function? Does this belong to the linear functional or bilinear functional? Remember, this guy is only a function of v, and this is a function of u and v. So this term, the red term over here, should belong to the bilinear functional. Right? It is linear with respect to both u and v. So if we need to define this with a non-zero v, then this bilinear form should be plus a boundary integral term. Oh, actually now I get to minus. That's like what Xing has pointed out. Because I'm now moving this to the left-hand side, I get a minus of b times u times v ds. Okay, so that gets me the proper Robin boundary condition. So to get to the right boundary condition, we may need to modify the linear functional. We may need to modify the bilinear functional. Whatever you need to do to enforce the proper boundary condition.